Hello students, today we will start learning the properties of the spread spectrum sequences. In the last module we have learned the generation mechanism of a spread spectrum sequence based which is a ML sequence based the linear feedback shift register architecture. We will continue our discussion today following the same architecture, and we will try to see the properties of the spread spectrum sequences generated by this kind of the linear feedback shift architecture, shift register architecture. Hope you will remember that we were discussing the structure to be of high speed form. Here I wish to mention one thing, that we initially constructed a generalized linear feedback shift register where there was a feedback from the last stage, which is the mth stage, to the initial stage, stage number 1, and all the feedback paths, I mean the XOR gates, were on the feedback path itself. In the high speed form, we shifted all those XOR gates of the linear logic gates. We came in the forward path, which is coming from the stage number 1 to stage number m in between, and CKs were the switches which were allowing the feedback of a particular stage to join in the to give actually the to add contributing to the feedback logic. Please note that when there was a generalized architecture, the notation of all the switches was C1 on the leftmost side and Cm minus 1 on the rightmost side. Once we have shifted towards the high speed form, the nomenclature for those switches should be changed, which is not done in the last module. Please correct it. Here I have corrected it already. The nomenclature of the switch should be C1 on the rightmost and the Cm minus 1 on the leftmost. All the equations that has been derived in till equation number 1.23 till the last module will follow the architecture that is given in this figure, that is with the switch nomenclature of C1 on the rightmost and Cm minus 1 on the leftmost. So, we also recall the fact that we have discussed the point where if A is a shift register generated sequence and B is another sequence generated by the shift register, maybe the initial condition for generation of A and generation of B are not same, and if we do the XOR operation in bit by bit for all the sequence of A, all the bits for the sequence of A with the all the bits of the sequence of B, we generated another sequence D. We also proved in the last module that the any bit in that generated new sequence D, which can be written in the form of CKAI minus K, where I is the ith pulse and K was actually the number of the pulses or the time instant you are going back from the ith instant, and Dj is the value stored in the jth stage of the new sequence D, that will be given by the XOR operation of CKAI minus K with CKBI minus K. After some mathematical simple processing, we ended up with the fact that CDJ can be actually written in the form of CKDI minus K, which proved a fact that any sequence generated by the linear feedback shift register and two sequences such two sequences generated by the linear feedback shift register and XORed on both of them, if you are generating a new sequence, each and every bit of that new sequence will keep a linear recurrence, will show a linear recurrence with the earlier stage values. So, this is the way, but the jth stage value of the newly generated sequence D is basically actually can be constructed by a linear recurrence of the stage values which are stored from the I minus k instant multiplied by their corresponding weight values or the switch values. This was an important observation with which we ended in the last module. In this case, we will continue from here to understand the further properties of the sequences that we are getting from this kind of the sequences. Apart from the fact that D can be generated by the same linear feedback logic as A and B, and then we can also think that the linear feedback register can also generate D. If A is a sequence generated by the shift register, the same construction can also generate the construction that is generating A and B, that can also construct a new sequence which is equal to D, and D is nothing but A XOR B. If my A and B, these two sequences are found to be exactly same, then obviously this XOR operation will give you all 0 sequence, and this all 0 sequence where then actually D, which is equal to A XOR B, will be exactly equal to all 0 sequence, because A is equal to B. And remember, such a sequence can be generated by any kind of the linear feedback shift register. And if you see that all the stages of a linear feedback shift register contains equal to 0 at some point of the time, then this will remain in the stage of the 0, and no more output sequences could be obtained from such kind of the architecture. And hence initialization of a shift register sequence of an architecture of a linear feedback shift register is very important, and never initialize a linear feedback shift register with all 0 values. Since we are discussing about a M stage feedback shift register, and we have seen in the last module, taking an example of M is equal to 3, that we could generate exactly 2 to the power m minus 1, that means in our case it was the 7 non-zero states. We could generate 7 non-zero states, and as it was generated by that, hence the period for this output sequence can never be greater than 2 to the power m minus 1, and this rule holds good for all kind of the linear feedback shift register of stage value equal to small m. And if you see that for a typical architecture, you are getting typical length or the period is equal to 2 to the power m minus 1, always the structure is generating 2 to the power m minus 1, then we call that the generated sequence is a maximum length sequence. Remember, I am repeating, the feedback shift register architecture can give you less than equal to 2 to the power m minus 1 number of the non-zero states. Hence, we are telling that the period capital N, if it capital N is denoted for the period, N will be always less than equal to 2 to the power m minus 1. And if by chance you see that N is equal to exactly 2 to the power m minus 1, the stage value is such that the period is equal to 2 to the power m minus 1, then this kind of the sequence will be called maximum length sequence or ML sequence. Very important kind of the sequence in the field of stress spectrum communication, because this is the, we will see later on that this is the mother of the sequence generation of any kind that we can think of till today. Linear feedback shift register sequence that is generating a maximum length sequence, if it is generating at all, then all of its non-zero output sequence will be maximal, and regardless whatever be the initial states. So, you keep on changing the initial states, all the non-zero states you will see it is the maximal one. And among the non-zero states, if you count, you will see that the number of zeros that you are getting, exactly the number of the zeros will be 2 to the power m minus 1 minus 1. Please go back and check the last module where we took the example of small m is equal to 3 and we generated a sequence where n is equal to 7 and which really actually signifies equal to 2 to the power m minus 1 status, and hence we can declare the sequence that we generated there was an ML sequence. Count the number of the zeros you are getting there, you will see you are getting exactly 2 to the power 3 minus 1 is equal to just 3 number of the zeros in the generated sequence. So, it holds good, it proves that for an ML sequence, if the number of the non-zero states, you will get the number of zeros exactly equal to 2 to the power m minus 1 minus 1, and hence the number of the 1 you will get how many? You will get 2 to the power m minus 1. Okay. And now, with the understanding of this fundamental property of ML sequence, let us see what will happen if we are having a maximum length sequence and we have a shifted value of this sequence. Let us assume that we have a shift of an amount j. So, A is generated by a linear feedback shift register. A is a binary sequence and it is an ML sequence also, and then we have generated another sequence AJ by giving a shift of an amount of j to A. So, AJ is a shifted version of A, and the shift is such that the shift is not equal to 0, and we have a modulo 2 to the power m minus 1, value of the j is such that, and then if I do the XOR operation of A with AJ, then you will definitely be sure that there won't be all 0 sequences. It will get, you will get some sequence again, it is not all 0 sequence. And since A XOR AJ, it is generated by the same shift register where from A was generated. So, definitely that A XOR AJ will be again an ML sequence. So, this is a very unique property of ML sequence. So, multiple ML sequences we can generate by giving a shift of the original sequence and doing the XOR operation in between them. And hence we are giving a cyclic shift of A. It is basically a with a cyclic shift of A we are XORing. And if we go ahead with the modulo 2 sum of this ML sequence and the cyclic shift of itself own sequence by some digit j, where j0 is not equal to 0 and modulo 2 m minus 1. So, the conclusion is that it will always produce another cyclic shift of the original sequence only. So, thing is that 3 facts. One is you have a ML sequence generated from a linear feedback shift register A. You have shifted it by an amount of the j where j is not equal to 0 and j is 2 to the power m minus 1, having modulo operation 2 to the power m minus 1. And if you are generating another sequence by doing XOR operation by bit of A with AJ, and you will be ending up with another ML sequence only, and that ML sequence that now you have generated by operation of A XOR AJ, luckily you will see that it is actually some cyclic shift version of A only. And that is, if I now write this in a mathematical form, how will it look like? I have taken A, I have shifted A by amount of j, I am doing the XOR operation, I am ending up with another k. Finally, this k is the amount of the cyclic shift of A, it is such that A, AJ, AK all are the ML sequences. Okay. But it does not mean that if you are having a non-maximal linear sequence and then if you do this kind of the operation, then it will be a cyclic shift of A. That is not possible, and it will not have the same period of A also. We can take an example to prove it. Suppose see this linear feedback shift register architecture where we have 3 stages. Unlike the first example where we took the feedback from the stage number 2, stage number 3 and we did the XOR operation, here we are having 2 XORs in the feedback path where the output from the first stage is also taking part in the feedback logic. We can see actually if you develop the table of generation the way we did in the last module for the other example, if you generate the sequence at the output, you will see that there are only 2 stages possible. You are getting any initial state value you start with, you will be ending up with only a period of 2, where the output sequence, one output sequence you will get like this, A is equal to 0 1 0 1 0 1 going on, and if you give a shift of 1 of this sequence, you will get another sequence 1 0 1 0 1 0. Now, if I try to do the XOR operation between these two, you will end up with all 1 values, which is never a shifted, some cyclic shifted version of the original sequence. So, it means actually there is no such value of the k exist for this example, for which this equation holds good. So, fundamental learning is, if you are not starting with a maximal linear sequence, you will never end up with another maximum length sequence by this operation governed by the equation 1.25. So, that proves that it is the strictly an unique property of ML sequence, but it does not hold good at all for any other kind of the non maximal length sequences. Now, coming back to the rest of the properties of this ML sequence. If we have generated an M sequence, the ML sequence is also called as M sequence for easy understanding. We will be calling it as M sequence throughout the course, and M sequence you will always find that it will include n plus 1 by 2 number of ones and n plus 2 by 2 minus 1 number of zeros. For example, where actually if you take the example of the last module, where small m was equal to 3, then you will see that we had 4 number of ones and we had 3 number of zeros. So, our period was 7 there, remember. So, there 7 plus 1 by 2, it was generating the 4 ones, and 7 plus 1 by 2, 4 minus 1, we had 3 zeros. So, 4 ones and 3 zeros we got in the sequence that we have discussed in the last module, and total period was 7. So, it also proves once again the sequence that we generated there is an ML sequence or M sequence. This property holds good for any kind of the M sequences. You keep on changing the initial value. I advise you to keep on changing the initial value on that architecture given in the last module, and check all these properties that today we are discussing to prove that really for the M sequence you will always end up with n plus 1 by 2 number of ones and n plus 1 by 2 minus 1 number of zeros. Next important property is the run property. What is run? Run is how many number of the subsequences of the consecutive identical numbers you are getting. For example, you are suppose generating a very long length ML sequence or M sequence, and in such a way that the sequence is coming like this. Like this, okay. Then run is, by run we say that how many consecutive same bits are coming. For example, for run property, if it is an ML sequence, it will contain at least one run of ones of length small m. What is the meaning? If I am having 3 number of the stages in the whole generated sequence, you will get at least one run constituting of value equal to 1, whose length will be equal to 3. So, you will get always a situation where consecutively 3 ones will appear. If your m value changes to say 7, then in the generated sequence you will get at least one occurrence of 7 ones coming parallelly, coming at a stretch. That is standard. You check it, you try to prove it with different value of initial situation and different value of the small m values, and you will realize. Then for the zeros, there is another rule. At least one run of zeros you will find. This is a run of 1. You will find at least one run of zeros for length m minus 1. So, if I am having m is equal to 3, so I will get at least one run of zeros where the 0 will be m minus 1 means equal to 2. That will appear simultaneously. It is consecutive occurrence actually. You should not count suppose 0 here and then another 0 here. Consecutively they should appear. And like this actually you will find the 2 to the power m r minus 2 runs of zeros and r minus 2 to the power m minus r minus 2 runs of ones with length equal to small r. So, length now if you keep on varying, length equal to 1, length equal to 2, length equal to 3, length is equal to m minus 2. If you keep on searching like this length, you will see that you are going to get m minus r minus 2 runs of zeros and m minus r minus 2 runs of ones automatically. So, if I now start searching actually whether I will get 1, if it is m is equal to 7 say, okay, shall I get actually 6 number of ones, how many times I will get 6 number of runs consecutively? It should be equal to 2 to the power 7 minus the length of equal to 6 minus 2 minus 7 minus 6 minus 2 kind of, and then you will get the runs of the zeros. So, if you are getting ending up with a positive value, if you are ending up with a positive value, then only you will get the existence of it, otherwise you won't get the existence of that. The autocorrelation property that we will discuss more in the next slides and next module, that autocorrelation property of this code sequence ML sequence, which is having the element of +1 and -1, in the discrete normalized fashion will be discussed by 0 to n minus 1. Suppose we have the n number of the observation samples and we are having a factor Cu is sequence ML sequence with us and nu is taking the delay of it. So, the autocorrelation will be talking about Cu minus u plus v into Cu. I mean you take the sequence and original sequence and you delay it, that original sequence, by an amount nu, and you take the multiplied value and average it over the number of the samples of that observation, and basically capital N is equal to the length of the sequence at least to take the autocorrelation function with the delay value is equal to nu. The cross correlation property is defined by this periodic discrete normalized cross correlation function, where actually there are two different set of the ML sequences we are taking and trying to find out how much they are related, how much matching is possible in between them. So, there we keep one sequence CJU and another one is CI, which is having with respect to u, which is having another shift or the delay of say nu, and again we are considering that both of them are having at least same length equal to capital N. If it is averaged over capital N, then this is the autocorrelation cross correlation of the ith sequence with the jth sequence for a delay of nu, we will tell. And if we find that this autocorrelation value of the two valued function with values phi 0 is equal to 1, and if it is a two valued only two valued, then it will be autocorrelation value will be 1 with the delay 0, and for delay 1 with for delay nu, it will be always minus 1 by n, and when your delay is not equal to 0. So, this minus 1 by n is a standard and well proven value for ML sequence. You take the cross correlation function of, you take any two ML sequences and try to find out the cross correlation value of it where your delay is not equal to 0. You will always end up with a standard value of minus 1 by capital N, where n is the length of both of the sequences, and there we are considering the both the sequences are having same length. So, you will always end up with a value of minus 1 by n. We will see it, we will prove it in the next module. Now, coming up with a little bit more about the properties. If you are considering about the M sequence with very large length capital N, which has an ideal autocorrelation function, which is similar to have a sequence of the Bernoulli random numbers. M sequences usually give you very near ideal autocorrelation property. What is the ideal autocorrelation property? Ideal autocorrelation property starts from the random binary sequence properties of the autocorrelation property of the random binary sequence. So, we find that ML sequence gives us a very close autocorrelation property, that of a random binary sequence. Cross correlation function of the M sequences, they contain the number of the peak values, which is side lobe values also, and they are diminishing if you are increasing the value of the capital N. So, if you increase the length of the sequence, you will get the cross correlation value peaks heavily down, which is a very good property for the code design, especially with related to the synchronization, where we do not prefer to have the multiple peaks. Then you will get a false lock in the detection of the synchronization, in detecting the synchronized points. So, these undesirable peak values of this cross correlation and the autocorrelation functions, that can be defined as this. Generally the subsets of any M sequences, they are selected in such a way that you can get always the best autocorrelation and the best cross correlation property. So, ML sequences are having the huge set, and you can actually have a flexibility to choose a pair of the good sequences, such a way that you get a good autocorrelation property, and I mean very high value of the autocorrelation property, and the cross correlation property goes almost close to 0. So, now there is we already understood that we do not prefer to go ahead with random binary sequences. That is why we discussed that why the periodic sequences will be preferable in from the view of the synchronizer design in the receiver circuit. That is why we entered into the linear feedback shift register, which helps us to devise a periodic sequences. Once we are dealing with a periodic sequence, we have to deal with the periodic autocorrelation. So, autocorrelation cannot have a single periodic function, cannot be a single periodic function. So, let us slowly enter into that periodic autocorrelation values. Suppose I have a binary sequence A, who is having the components drawn from the Galvez field 2. We have the components AI and they are drawn from the Galvez field 2. We understand if it is a Galvez field 2 component, it can have only two values, 0 and 1. Let we can mapping that 0 and 1 value in a binary antipodal sequence P in such a way that for 0 we will get -1 and for 1 we will get +1. So, mathematically I can generate every component of this Pi by taking -1 whole to the power ai plus 1, or you write Pi equal to minus a whole to the power ai. We can give a proof. See, if ai is equal to 0, ai can have two values, right? Ai can be either 0 or 1. So, when ai equal to 0, Pi will be -1, and when ai equal to 1, it will be when ai equal to 0, it will be +1, and when ai equal to 1, it will be -1. So, you can generate all the values of the Pi based on the value corresponding to the value of ai. So, there is a direct mapping. Now, when we talk about the periodic autocorrelation of the periodic binary sequence A, we are considering that suppose the period that is associated with this binary sequence A is capital N, and we can define now the periodic autocorrelation of this P is equal to, for a shift j, is equal to Pi plus j and averaged over 1 by n. So, as if Pi is one set, Pi plus j is a shifted version of this, by shift is by j, and then this is a periodic autocorrelation function for the period of capital N is yielding. And if I substitute now the values of Pi and Pj from here, I will be ending up with -1 whole to the power ai for Pi into -1 whole to the power ai plus j for Pj, Pi plus j, and hence this is the final expression we are ending up. And basically this is nothing but we understand that there is no over a Galvez field 2, there is no existence of simple addition. Basically all are the modulo 2 operation or the XOR operation, and this whole expression now can be written as, especially after summation, it can be simplified in the form of aj minus dj. This AJ denotes all the number which agrees with the corresponding bits of A. That means, AJ is equal to number of the zeros and DJ is the number of the ones, and the relation between them should be like this. DJ will be n, capital N minus AJ, which is equal to the number of ones in n. For any number, for any period capital N, this equation holds good. Now, question is from the consideration that A XOR operation with AJ, which yield will definitely yield AK, because we have already seen this proof earlier with when J is not equal to 0. If it is an ML sequence, definitely it will do like this, where A, AJ, AK all will be ML sequence, and if J is not equal to 0 and J is modulo 2 to the power m minus 1, and then it follows that all the AJs, that means if this equation holds good, then AJ will be always equal to the number of the zeros in the maximal sequence, if J not equal to 0 modulo capital N, and thus we will be ending up with a value of n minus 1 by 2. Similarly, it will be also n minus 1 by 2 if J is not equal to 0. And herefore, then if we substitute these values in the equation of the theta pj in the last slide that we have shown, for J equal to 0, the theta p value, there will be perfect correlation and the correlation value will go up to 1. And if it is not equal to 0, if you substitute there the values of AJ and DJ, you will end up with a value of minus 1 by n. So, here is that autocorrelation value that we blindly stated as a property of ML sequence, that autocorrelation, the cross correlation, when J is not equal to 0, that means you are plotting the cross correlation values. If it is a cross correlated value output, then we will be ending up with always minus 1 by n. Remember this periodic autocorrelation function xt, if the xt is having a period of t, there is a classical definition for computing the autocorrelation, periodic autocorrelation of a periodic function xt given by xt plus tau, and the where integration is running from c to c plus t. The c is an arbitrary constant, it can be 0 also in your analysis at any point, and basically it is the integration over one period interval over which the xt is lying. And the autocorrelation function, by default, if you are computing this, it is obvious that the autocorrelation function also will lie over a period of capital T only. In the next slide, we will derive, in the next module, not the slide actually, in next module we will derive the periodic autocorrelation, and the periodic autocorrelation we will try to now find out with respect to the PT. We will assume that ideal periodic spreading waveform and infinite extent with rectangular chip imposed on it will be the assumption, and we will see how the periodic autocorrelation of PT will look like, the spreading sequence that will look like.